Hey everyone, this video is going to look at the world of climate change, which of course is a hot topic, no pun intended, but a topic that has wide-ranging biological implications that affect not only our species, but really most species across the globe. And we'll review some of the key points that surround this idea of climate change and what it is that we know about it. Obviously, as the name suggests, there are climates across the globe, and these climates are somehow or other changing, and we can detect these changes. What do we know about climate, and what do we know about the way that climate can change? Well, first of all, in order to understand climate change, it's kind of important that we understand what the definition of climate is. And climate really, quite basically, is a statistical characterization of the kind of climate system that an area has. Well, what's a climate system? A climate system is something that is influenced by basically most aspects of the Earth's geosphere. So, an area's climate does broadly characterize the weather patterns that are sort of typically associated with various parts of the globe. And these weather patterns are being dictated by things like the Earth's atmosphere and the way that changes, and the Earth's hydrosphere and the way that that changes, which also interacts with things like the Earth's cryosphere. And there's also an interaction between these systems and the Earth's lithosphere, and also there's a component of the biosphere that's related to this. So all aspects of the Earth's geosphere are really related to climate systems. And as you might recall, global atmospheric circulation is really something that drives climate. So we can talk about how there are different patterns in the way that air cycles through the Earth's atmosphere, whether this is warm equatorial air or cool polar air, and variation in the movement of these air masses across the globe are what really do drive climate patterns. So, first and foremost, we kind of want to get at an understanding of what climate is. It's basically related to climate systems. And we know that Earth's climate varies a lot globally. And in fact, folks have attempted to define all of the different climate regions of the globe in some fairly detailed ways. This here shows the Köppen climate classification system. And this is a characterization of Earth's climate that was made up by people, but it turns out to be fairly accurate. If we are to compare the climate of one region of the globe to another, oftentimes we can find sort of predictable and measurable differences in the way that the climate of different parts of the globe can be characterized. And in fact, there are lots of nuanced little patterns and lots of nuanced little variation in the types of climate that different parts of the globe have. But we know generally that these patterns, again, are being driven by patterns in atmospheric circulation, and also to a certain extent patterns in how the Earth's oceans are circulating water around. What we also know about Earth's climate is that it's been changing for a long time. And so there might be a common misconception that climate change is only really a new thing and that it's only really being caused by human activity. But that's in fact not true. Climate change was happening long before modern humans even evolved. How do we know this? Well, there are records of carbon dioxide concentrations in ice cores, for example, that illustrate how carbon dioxide concentrations have changed over some pretty substantially long time periods. And we know that there's a correlation between carbon dioxide concentration in the atmosphere and temperature. Higher carbon dioxide concentrations tend to be correlated with higher temperatures. And so we can take a look at how carbon dioxide concentrations in the atmosphere have fluctuated going back something like 800,000 years and make inferences about how those periods of time were also related to changes in Earth's temperature. And as we can see, there have been sort of periodic shifts between uh, times when temperatures on the Earth were relatively warm and times when temperatures on the Earth were relatively cool. And it just so happens that the present represents a time period where the Earth's temperature is relatively warm. But it hasn't always been that way. And these fluctuating temperature patterns seem to have been occurring for, again, really long periods of time. We also know that the Earth experiences something called Milankovitch cycles. And basically, these cycles represent the fact that Earth's orbit around the sun isn't always entirely consistent. Sometimes the Earth's orbit around the sun is a little bit more elliptical, and that causes the Earth to basically be distributed a little bit further away from the sun than it is normally. And that happens periodically over pretty large time scales on the order of hundreds of thousands of years. Every so often, there's this pattern called eccentricity, where the Earth happens to get a little bit further from the sun than it normally would during its orbit, and that causes the Earth to cool a little bit. And this is part of the reason why we see these fluctuating changes in Earth's temperature that happen sort of periodically and sort of predictably. Earth also kind of changes its wobble. And the Earth might change its wobble every 20,000 years or so, and that can affect the way that different climate patterns occur on the planet. And Earth also changes the way that it's tilted on its axis. So the Earth is generally characterized as having a 23.5 degree tilt on its axis, but about every 41,000 years, that axial tilt does change a little bit. And variation in axial tilt also causes the amount of solar insolation to hit the planet to vary. And as the amount of solar insolation that hits the planet varies, that also causes climate to change. So there are multiple reasons why the climate on Earth can change naturally. And this has probably been happening for a very long time, if not for the entirety of the time over which the Earth has existed. And these, again, are natural climate shifts. The Earth also has a pretty long history of ice ages. So again, we know that there have been subsequent, or rather periodic shifts in Earth's temperature. There have been warm periods and cool periods. And as it turns out, these cool periods are often associated with ice ages. There, again, is information about this that has been obtained from studying ice cores and studying the concentration of carbon dioxide in ice cores that can be dated. And in fact, this record goes back something on the order of about 2.5 billion years, where we can make inferences about periods of time where the Earth's global average temperature was relatively low and periods of time when that average temperature was relatively high. And if we look at this record going back here, something on the order of about 2.4 billion years, we can see that there have been periodic changes in Earth's temperature, and some of those periods of time are associated with different ice ages. And if we look a little bit more recently at how the Earth's climate has changed in the last 450,000 years, we can see that there have been periodic transitions between so-called interglacial cycles and glacial cycles. And as we can see, about 50,000 years ago, the Earth was in a glacial cycle, but more recently, that glacial cycle has come to an end, and we are now in an interglacial cycle. And so this image on the top left illustrates what the maximum extent of Ice Age continental and sea ice was probably like during the last major glacial period, compared to what the distribution of sea and continental ice looks like today. And it's, of course, much different. There's not a whole lot of continental or sea ice remaining, but once upon a time there was. But we can also see that there have been these periodic shifts back and forth between interglacial and glacial cycles that have been happening for hundreds of thousands of years. And these shifts are associated with significant temperature changes that the Earth has experienced. And so, again, all this illustrates that climate change is nothing new on the planet. There's evidence that it's been happening for a long time. And in fact, it almost seems to be happening at somewhat predictable rates. It just so happens that currently we are in a warming period, which the Earth has been on a trajectory of warming up sort of naturally anyway, despite the fact that humans are around contributing to that. And the Earth has been a relatively warm environment anyway, and that's generally because of this thing we call the greenhouse effect. So solar insolation, sunlight coming into the Earth, sunlight being absorbed by the Earth, and the presence of these things we call greenhouse gases in the Earth's atmosphere all contribute to keeping the Earth relatively warm. And basically, warm air can get trapped within the Earth's atmosphere. It heats up the surface of the Earth. That air can rise, but that Earth can become trapped within the atmosphere, and it keeps the Earth relatively warm, a lot warmer than outer space is. And this actually turns out to be extremely important because without the greenhouse effect, the Earth would not be a habitable place. And so life probably wouldn't exist without the greenhouse effect. However, you probably have heard about greenhouse gas emissions, and this is a situation where there are certain gases that are known to increase the greenhouse effect. That is, high concentrations of certain kinds of chemicals or certain kinds of molecules tend to magnify the influence of the greenhouse effect and make the Earth's uh, atmosphere a little bit warmer than it would be naturally. And these kinds of gases, not surprisingly, are things like carbon dioxide and methane, and to a lesser extent, things like nitrous oxide and some fluorinated gases. But particularly, carbon dioxide is one of the most widespread greenhouse gases that's distributed across the globe, and most carbon dioxide is a byproduct of burning fossil fuels. And to a lesser extent, we see that methane makes something of a contribution to greenhouse gas emissions as well. And some of that might be coming from using things like natural gas, or it might even come from things like landfills where certain organic compounds are decomposing, or even from agricultural animals who expel methane as part of their digestive processes. So anyway, this is what the greenhouse effect is, and it is an important part, an important natural part of the Earth's climate systems, and an important natural part of keeping the Earth habitable. But lots and lots of greenhouse gas emissions, lots of carbon dioxide emissions, tend to make the concentration of greenhouse gases in the Earth's atmosphere a little bit higher than they have been naturally in the past. And this contributes to making the Earth a little bit warmer than it has been in the recent past. And what are the sources of these greenhouse gases? Well, a lot of that again comes from combustion, from burning fossil fuels. We know that fossil fuels will readily react with oxygen, sort of like sugars will readily react with oxygen during the process of cellular respiration. Same things happening during combustion. And the byproduct of combustion is typically some exhaust, and that exhaust is usually carbon dioxide, and also heat is released in the process of combustion. So not only is there heat naturally released during combustion, but greenhouse gases are released during the process of combustion. And as I mentioned, a lot of organic wastes that get deposited in landfills do eventually decompose and release things like carbon dioxide or methane, and those are again potentially harmful greenhouse gases as well. Once they accumulate in the atmosphere, they start to make the Earth's atmosphere warm up a little bit more than it would naturally. So, how has human impact contributed to elevating greenhouse gas concentrations on the planet? Well, we know that basically this increase in greenhouse gas emissions, or this increase in greenhouse gas concentrations in the atmosphere, is driving a process you've probably heard of known as global warming. And this is basically when the Earth's atmosphere starts to heat up more than it would naturally because of the presence of these chemicals in the atmosphere. And how do we know this is related to human activity? Well, we have data on this. The graph here on the right shows a time frame going back about 2,000 years, and some of this information is inferred. And the axis on the right, I'm sorry, the axis on the left shows the concentration of carbon dioxide and nitrous oxides. They're in different units. Carbon dioxide shown in ppms, which is parts per million, and nitrous oxides are shown in parts per billion. So parts per million are larger units than parts per billion, if that makes sense. And on the right side of this graph, we have methane shown in parts per billion. And then each of these different colored lines represent the relative concentrations of these three different greenhouse gases going back over this long period of time, 2,000 years. And what we can see is that the concentration of these three greenhouse gases has remained relatively constant for a pretty long time. There's been some fluctuation in the concentration of these things that has happened naturally because of natural Earth processes. Maybe things like volcanism might have contributed to changes in the concentrations of these chemicals, for example. But by and large, their concentrations haven't changed a whole lot, and they've never risen to alarmingly high concentrations as far as we can tell looking back over a pretty long record of through a pretty long period of time. However, starting around the year 1800, 1900, we see that there's a significant increase in the concentration of all three of these greenhouse gases. And we can ask questions about, well, what was going on the planet Earth during the 19th and 20th centuries that contributed to increases in the concentrations of these chemicals? The Industrial Revolution, that's right. And so via the Industrial Revolution, we start seeing widespread use of fossil fuels for energy sources. And as those fossil fuels are being combusted, high concentrations of greenhouse gases are starting to be released into the Earth's atmosphere, causing their concentrations to have become way higher than they ever were in the past. Concentrations of carbon dioxide never really used to be much higher than about 280 parts per million or so, but all of a sudden, starting about 150 years ago, we see that the concentration of carbon dioxide in the Earth's atmosphere has skyrocketed up to something close to 400 parts per million. And that's a lot. And we can see similar changes in the concentrations of things like nitrous oxides and methane, both of which also had concentrations that were closer to 250 parts per billion, going back over the last couple thousand years to in just the last 1 to 200 years, the concentrations of those greenhouse gases have likewise skyrocketed to something on the order of about 1,200 parts per billion for methane and something on the order of close to 400 parts per billion for nitrous oxide. So human activity seems to be pretty tightly correlated with very significant increases in the concentration of greenhouse gases. And what do increased concentration of greenhouse gases do? They cause the Earth's atmosphere to become warmed a lot more than it would naturally by the greenhouse effect all alone. And this is what causes this thing called global warming. Another contributor to global warming has to do with the reflectivity of the Earth's surface. And we call this reflectivity albedo, or also known as the albedo effect. And albedo basically represents the fraction of light that the Earth's surface can reflect. And different surfaces have different amounts of reflectivity. And so we can measure albedo on a scale of 0 to 1. Albedo of 0 means the surface doesn't reflect light at all. And albedo for light surfaces is close to 1 because light surfaces are completely reflecting light. This isn't surprising. A black surface will absorb a lot of light, whereas a white surface will reflect light. You've probably noticed this. And so certain surfaces on the Earth's certain surface features of the Earth have different albedos. Surfaces that are relatively dark tend to absorb a lot of the Earth's light, whereas surfaces that are relatively light, like ice or snow, for example, tend to reflect a lot of light. And in fact, as it turns out, having a lot of the Earth covered by ice and snow reduces the albedo effect and can keep the Earth from absorbing a lot of heat and packing that heat in within the Earth's atmosphere. And so albedo can help reduce the greenhouse effect, really can help reduce global warming. However, as more and more global snow and ice is melting, there is less and less of the albedo effect. And so we're seeing more and more of the sun's energy being absorbed by the Earth's surface, causing the Earth to warm up a little bit more. We can see an example of snowpack in the Rocky Mountains of Colorado, where 30% loss of snow albedo was caused by dust. And so by a virtue of areas presumably maybe being overused for agriculture, and then the surface layers of those agricultural areas being blown onto snowfields in the nearby Rocky Mountains, those snowfields that were once very light colored and reflected a lot of light now have been found to start absorbing a lot of light, causing not only the Earth's surface to absorb more heat, but causing a lot of that snow to melt. So there's kind of a combined effect of this dust on loss of albedo. So albedo turns out to be yet another important thing that naturally helps the Earth. I should say another thing, but turns out to be a thing that naturally has helped the Earth mitigate solar insolation, the effects of warming due to solar insolation. We also know that the temperature of the Earth's atmosphere has been rising quite significantly in the past decades, and it's been rising kind of a lot more than we really have any record of in the distant past. Obviously, we are already in an interglacial cycle, so we would expect the Earth to be warming naturally as it is, but as it turns out, this is kind of happening maybe more so than one might expect. Certainly, maybe more than scientists might have expected. And in particular, it turns out that in the last 50 years or so, cold records used to be the dominant theme on the Earth. So areas that experienced increasingly cold conditions that set records were observed more often than areas that received increasingly warmer conditions that were setting records. But starting about 25 to 30 years ago, that trend switched to where warm records started to outpace cold records. And now we're seeing more incidences of extreme heat than we are of extreme cold, which used to be the situation observed in the past. And this is all based on empirical data, actual observations that people have. And that's what's shown with the thick dashed lines. The blue lines represent the cold records, and the red line represents the warm records. And if we look at the thin red line, what we see are these 10-year trailing averages of the percent of Earth's surface that is basically experiencing these records. And in particular, what's alarming is the fact that in recent data, we see that more than 13% of the Earth's surface is experiencing increasing warm records. And there's really no record of anything like that happening in the past. And so this is really alarming. What is causing the Earth's surface to be experiencing so much warming? Well, a lot of it has to do directly with these greenhouse gas emissions, and these greenhouse gas emissions contributing to the greenhouse effect causing global warming. And what is causing the release of greenhouse gases? It's mostly burning fossil fuels. And so we can start looking at climate change projections. Well, we know climate change has been happening on the Earth for a long time, but what do we predict? How do we predict climate change might unfold in the future? And all evidence points towards, well, the most important contributing factor to climate change in the future is almost certainly going to be carbon emissions. And so we can start asking questions about, well, how would different projected scenarios of carbon emissions likely contribute to changes in the Earth's global temperature? And so that's what climate scientists have done, and they have generated these different models known as representative concentration pathways. And these have been developed by the IPCC, which is the International Panel on Climate Change. And these different representative concentration pathways, or RCPs, basically represent different models that are related to different concentrations of carbon-based emissions into the Earth's atmosphere. And there are 4 different models shown on this graph at bottom right: RCP 2.6, 4.5, 6.0, and 8.5. And what we can see on the graph is time on the x-axis and carbon dioxide concentrations on the y-axis, again shown in parts per million. And this starts at the year 2000, and the projection goes forward into the year 2100. So what these different RCP models show are what the concentrations of carbon dioxide are expected to be in the Earth's atmosphere with different amounts of carbon emissions by human activities. So RCP 2.6 really represents the most ideal scenario. If fossil fuel burning was to stop today and we really stop depending upon carbon-based fuels, then we might expect that the concentration of carbon dioxide in the atmosphere would increase a little bit into the future because of a bit of a lag effect, but then it might start to level off and kind of remain around about 400 parts per million, which is where it's at presently. We kind of know that also from looking at this graph. We can see the concentration of carbon dioxide is at about 400 parts per million. If instead we don't do anything, or we try to do something, then we see some of these other models. And so RCP 4.5 is a moderate emissions reduction scenario where maybe there's some amount of reduction in carbon emissions, but not entirely. Then we would expect to see the concentration of carbon dioxide go up, as it's already doing, and maybe stick around about 550 parts per million and stay there. In contrast, if we really just keep burning fossil fuels and allowing carbon emissions to persist, the concentration of carbon dioxide in the Earth's atmosphere could reach as high as 700 parts per million. Or if we really just ignore this situation altogether, then that's what's called RCP 8.5, which is kind of the worst case scenario. If carbon emissions just continue unchecked, sort of unmonitored, the concentration of carbon dioxide in the Earth's atmosphere could reach as high as 1,200 parts per million, which is kind of ridiculously high, but that's the direction that we are headed in if we don't start doing something about reducing our carbon emissions and doing something about it kind of fast. This is a very realistic possibility for the future of our planet. Why does this matter? How might this impact global warming? Well, this map here at the top illustrates what the projected changes in the Earth's temperature would be under these two contrasting carbon emission scenarios, RCP 2.6 and 8.5. With RPC 2.6, we see that global temperature changes won't be too severe. There will be some changes, and notice all of these changes are positive increases, so that means temperature would be predicted to increase a little bit globally, just about everywhere, even under RCP 2.6, which isn't surprising because the concentration of carbon dioxide is still hovering around 400 parts per million, which is a lot higher than it's ever been in the historical past. And in particular, the polar regions would have the most negative impact of this, the largest temperature change. However, in contrast, if we look at what global temperature change could be like under RCP 8.5, we see that it really is a doomsday scenario, and that global temperature change is expected to be somewhere between maybe 10 and 15 degrees in just about every single part of the globe, especially at the poles, where we see the highest amount of temperature change still. And this is pretty bad. This is a situation where natural biomes and natural ecosystems would all potentially be affected by significant increases in global temperature, causing changes in normal ecosystem processes, causing changes in climate, causing changes in the way that normal kinds of atmospheric processes are happening, which directly could affect the way that normal ecological processes could be happening, which could directly impact the distribution of different species, many of which we depend upon for our own survival as food sources. This could impact the availability of fisheries as a food source. This could impact the availability of suitable habitat for agricultural crops, for example. This could impact the availability of suitable habitat for human populations who might have to migrate away from parts of the planet where conditions might start to become too warm to become habitable any longer. And this can start to lead to other devastating effects like increases in disturbance regimes, such as the magnitude and severity of wildfires, the frequency of wildfires, certainly, again, loss of suitable habitat for particularly sensitive species who don't do well in super warm conditions, that didn't evolve in super warm conditions, and who are maybe incapable of adapting to super warm conditions. And all of this very much could happen simply because of uncontrolled burning of fossil fuels, causing carbon dioxide concentrations to become increasingly higher and higher in the Earth's atmosphere. So, how do we know that any of this actually could happen? Well, climate scientists have put a lot of time and effort into trying to model climate change projections. Obviously, the representative concentration pathways are some pretty nuanced models. If you go read about them, you'll learn that chemists and physicists and biologists have all gotten together and tried to come up with the best guess they can about how burning fossil fuels can contribute to increased carbon emissions. But another thing that folks have done is taking some kind of sophisticated computer modeling methods and use them to see how well and how accurately they can project changes in climate. How have they done this? Well, folks have taken climate records from the past 100 or so years that are based on empirical observations. So we know that, for example, in this particular graph here on the left, that Earth's temperature on average has kind of increased somewhat, not a ton, but it has increased somewhat. And then we can start making projections based on how Earth's temperature might continue to increase depending on these different emission scenarios, high emissions, intermediate emissions, and maybe relatively low emissions. And then folks have taken those same computer simulations and used them to basically retroactively go back and see how well those modeling schemes fit actual empirical data from the past. And so this dark green line here is a computer model that retroactively is attempting to predict what past temperature would have been like on the Earth going back about 100 years. And the question scientists asked was, if our model accurately can show how temperature has changed in the last 100 years, then it's probably a pretty good predictor of how temperature is going to change into the future. And lo and behold, here we see that the computer model matches the empirical data from the last 100 years very well. And so this provides confidence in our estimate that the changes in the Earth's temperature is likely to follow one of these different projected scenarios, depending on what the level of carbon emissions turns out to be. And we can take a similar approach to looking at how the Earth's temperature is projected to increase with and without human influence. And so it looks like we're already in a naturally warming period. And that's sort of what's shown here with this blue line on the bottom on this graph at right, where over this period of 100 years, there's been a little bit of an increase in temperature we've seen that would have happened naturally, whereas the pink line sort of shows what that temperature change has been with human activities. And it seems like, yeah, the Earth's temperature it has been increasing already as it is, probably because we're in an interglacial period. But with human activity, particularly burning fossil fuels, contributing to carbon emissions in the atmosphere, we're seeing that the Earth's temperature is increasing even more than it would have naturally because of human impact. And this, again, is a pretty alarming scenario and a very, very realistic scenario. So even if people try to brush all this aside and say, oh, it's just pure postulation, it's just supposition. I'll even go so far as to say people might want to call this a hoax. Well, all of the best evidence that we have sitting in front of us points toward the fact that this is anything but supposition and anything but a hoax, and it is a very, very real situation. The Earth's temperature has been rising, and there is a direct correlation between increasing temperatures and carbon dioxide emissions, and increasing use of fossil fuels is only projected to be directly correlated to increasing Earth's temperature or global warming. Now, as I mentioned, climate change is something that is likely to have an influence on species distributions, and you might be thinking, well, how do we know that? Well, we already know that from historical records. And the kinds of historical records we have turn out to be kind of interesting. There are these rodents known as wood rats in the genus Neotoma, and these wood rats are also known as pack rats. And they've earned the name pack rats because they have a habit of going around the environment where they live and collecting all kinds of different material and taking it back to their nests. And they might do different things with this material. They might use it for food, or they might use it for insulation. And then oftentimes when these wood rats are done with whatever material they've collected from the environment, they'll discard of that material in a waste pile. And in that waste pile, they'll also defecate and urinate. And effectively, they are urinating all over a lot of disposed material that they've collected from the environment. Things like plant material, or sometimes pieces of small insects, or even pieces of bones. But more often than not, these wood rats tend to collect plant materials. As it turns out, in particularly dry environments, that plant material, after it gets urinated on, can fossilize into this stuff shown in this little image here on the right that's called guano. So this is a piece of a fossilized wood rat midden. And these fossilized wood rat middens can survive for really, really long periods of time, particularly in dry environments. In fact, they can survive for tens of thousands of years. And if clever scientists can collect this fossilized midden material and figure out what kinds of plant species were in it, that is, what kinds of plant materials were those wood rats collecting 10, 20, 30, 40,000 years ago, they can start to piece together a picture of what the vegetation was like in those areas at these particular points in time. And then you might be asking, well, how do these scientists know how old this material is? They use radiocarbon dating. And so there are radioactive isotopes of carbon that occur naturally in all living things. And carbon has a predictable half-life. That is, radioactive isotopes of carbon have a predictable half-life. And so by basically figuring out the concentration of that particular isotope of carbon in a particular material, you can figure out how long it's been since that material was alive. And so that's what scientists have done with the material collected from these wood rats, this fossilized guano. And so clever scientists have taken this fossilized material, identified the kinds of plants that comprise this fossilized material, and dated that material to figure out how long it was since those plants were alive. And that gives us something called a midden series, which is shown on the left. And so this midden series represents time on its y-axis, going from the present back about 60,000 years. And then we have, in this example, four different plant genera: firs in the genus Abies, junipers in the genus Juniperus, pines in the genus Pinus, and oaks in the genus Quercus. And this was recorded at a wood rat midden in northern Baja California, so not too far from Southern California. And what we see is that between about 10,000 and 20,000 years ago, coniferous species were very, very common in this wood rat midden. And that's evident by the length of these bars. These bars represent the relative frequency of plant material that was assigned to these different genera. And so the x-axis of this midden series represents the relative abundance of these plant materials, going from not very abundant to very abundant. And so we see things like firs and junipers and pines, which are all conifers, were really common at this site between 10 and 20,000 years ago, but almost entirely absent now. And by the way, this particular site is in the desert, and coniferous species are really uncommon in the desert now, but the evidence from this wood rat midden shows that once upon a time, these coniferous species had pretty widespread distribution in this area, pointing towards the fact that the climate of this area was a lot different 10 to 20,000 years ago. It wasn't always a desert. It was probably a cooler, wetter environment 10 to 20,000 years ago that could support coniferous species. And this information corroborates with the fact that going back into the more distant past was a glacial period. And we are just now entering an interglacial period, which is why this environment is probably devoid of conifers at the moment. And scientists have pretty cleverly studied these wood rat middens all over North America and used this information to infer that the distribution of conifers, something like 8,000 years ago, was a lot more frequent than it is now. And so we can see this map here, which represents California on this side and Nevada on this side, and these black blobs represent the distribution of oak juniper woodlands. We can see that those oak and juniper woodlands had a pretty wide-ranging distribution, something like 8,000 years ago, and that they were at relatively lower elevations, something like maybe down to 900 meters in elevation. The second map shows that by about 2,000 to 3,500 years ago, their distributions had contracted and they were only found in wood rat middens above 1,200 meters. And that now in the present, we only find those same oak and juniper communities at elevations above about 1,400 meters. Why are we looking at this? We're looking at this because we know that species distributions can change as an artifact of climate change. And this can happen naturally as the climate changes naturally. And if we know that species distributions can change as the climate changes naturally, then we probably should put confidence in the fact that species distributions can also change if the climate changes unnaturally or if the climate changes because of human activities. And so we can start asking questions about how are future climate change scenarios likely to influence the range of particular species. And we can do this using some pretty sophisticated computer modeling tools that are somewhat beyond the scope of our class to discuss. But effectively, we can take a lot of information that we know about where species presently have suitable habitat, and there's a lot of data out there on various aspects of the climate. And those are the data that were used to generate these particular models here. These are known as species distribution models. And if we can take information about where species occur and couple that with information about the environmental conditions where those species occur, then we can make predictions about where those species are expected to have suitable habitat. And that's what these maps show. The colors on these maps represent the amount of suitable habitat that exists for a particular species that we're looking at here, which is known as ashy silk tassel. And the areas with really low values represent areas where there's not very much suitable habitat for ashy silk tassel. And as we see the colors change from pink to orange to yellow to green, we're seeing areas where the habitat is increasingly more suitable. So habitat suitability is measured on this scale going from 0 to 1. And then all of the little green dots on the map represent areas where this species is known to occur, and those were the observations that were used to make the model. So not surprisingly, areas where the species has really high suitable habitat are areas where that species occur, but we can look at other areas where we don't have information on the species, or we don't have observations of the species, where we would predict that the species does have a suitable habitat. And the map on the left, which by the way shows California, Nevada, a little piece of Utah, and basically Western Arizona, uh, is the area of suitable habitat for ashy silk tassel that was measured in the year 2022. Then we can take information about what we think is going to happen to the Earth's atmosphere, or rather the temperature of the Earth's atmosphere, under the RCP 4.5 emission scenario. And recall, the RCP 4.5 scenario is a moderate projection if humans make an attempt to try to reduce greenhouse gas emissions. We would project that the influence on increased global temperature wouldn't be nearly as bad compared to if we don't do anything about it. And so this map on the right shows what the extent of suitable habitat by the year 2070 would be for ashy silk tassel under the RCP 4.5 emissions scenario. And what you can pretty clearly see from comparing these two maps is that this species is predicted to lose a lot of its suitable habitat, particularly at the southern latitudes of its distribution range, which isn't terribly surprising if we expect that more southerly latitudes, which are already kind of warm, naturally are going to become even warmer under the RCP 4.5 emission scenario. And also, if you know anything about the geography of these maps, some of these areas where we see the species projected to have increases in suitable habitat are mountain areas, areas at higher elevations. And so these projections allow us to generate a prediction about how a plant species like this, but also many other species, are expected to undergo range shifts. They're probably going to have to migrate upwards in elevation or further north in latitude in order to be able to occupy areas of suitable habitat. And that's not terribly different than what we saw going on with the contraction of these oak and juniper woodlands that also appear to have lost suitable habitat at lower elevations and only now occur at higher elevations as we've entered this interglacial cycle. So Evidence from the distant past tells us that species can change their distributions as the climate dries out and warms up, which is what has happened here in Western North America in the last 60,000 years. We have evidence to show it. And looking forward into just the next 50 years, we can see that there's expected to be pretty rapid changes in the extent of suitable habitat for things like ashy silk tassel, which is just one example of a plant species that occurs in mountain environments. We can make predictions about how this might happen to all kinds of other mountain species as well. So there's been a lot of focus on how greenhouse gas emissions contribute to increases in the Earth's atmospheric temperatures, but we can also ask questions about, well, how might climate change influence precipitation patterns? And we also have models that have allowed us to reconstruct past patterns in precipitation. And this model here shows a record going back about 18,000 years, and this is data for the climate of the Mojave Desert in California. And each different line represents the amount of precipitation that was retroactively projected to have occurred in the Mojave Desert at different times of the year, during the winter, during the summer, during the spring, or during the fall. And we can see that there's been variation. There probably was some variation in those precipitation patterns at these different times of year, but by and large, we see that they have certainly changed. And in fact, one thing that we notice in particular is that once upon a time, summer rainfall was a lot higher in the Mojave region than it is at present, and than it might have been in the distant past. And this illustrates that as the last glacial cycle ended, and we have now started to enter an interglacial cycle, or an interglacial period, I should say, as the last glacial period ended, and we now are entering an interglacial period, we are seeing changes in the precipitation regimes within this particular area, where most of the precipitation that falls is in the winter, whereas in the past there was a lot more spring precipitation and a lot more summer precipitation. So climate change, in the absence of human influence, can influence or can affect precipitation patterns. So then, how is human-induced climate change likely, or how are human effects on climate change likely to play in to how precipitation might change? Well, in general, warming of the Earth's atmosphere is associated with increases in evaporation. And so with warmer air temperatures, water will evaporate faster. And that leads to greater water vapor concentrations in the Earth's atmosphere, which means there's more water available to potentially condense into rain. And so this means that some areas of the globe might actually see increases in rainfall, but other areas of the globe might. And so the distribution of precipitation globally could, in fact, change quite a bit. And this map here attempts to illustrate what the changes in the Earth's precipitation patterns are likely to be by the end of the 21st century. And the scale bar on the right illustrates areas where we might we might expect to see decreases, kind of going from this part of the scale down. So these are all negative values, and areas where we might expect to see increases going from this part of the scale bar up with positive values. And so many regions of the globe, shown with these warmer orangish colors, are expected to have decreases in temperature, for like California, for example, or maybe parts of Central America that used to get a lot more rainfall on a regular basis might become drier than they have been in the past, or parts of South America might become drier than they have in the past, or places like Australia might become drier, or parts of the Mediterranean region might have a lot less precipitation than they have historically, whereas places like maybe Indonesia or the Western Amazon basin might start to get a lot more precipitation than they had historically. So climate change not only has to do with changes in the temperature of the Earth's atmosphere, but changes in the precipitation patterns, which are also directly related to Earth's atmospheric patterns. And another topic folks often discuss in the context of climate change is sea level rise. And there are a couple things going on that can cause the Earth's sea level to rise. One of them is the melting of glaciers, and the other is thermal expansion of water. So we have evidence to show, for example, that the McCall Glacier in Alaska used to look like this on the order of about 80 years ago or so. And nowadays, or in the early 21st century, this glacier had significantly retreated. Where is all of that water going when it melts? It goes into the ocean. And so this contributes to sea level rising, and it not only causes land area to be lost, particularly in coastal environments, but it poses a threat to nearshore marine ecosystems and also to some freshwater ecosystems as well. And that could have potentially negative consequences for coastal industrialization and coastal urbanization and the economic pursuits that people are engaged in coastal areas, which, by the way, where are most human populations settled? That's right, in coastal areas. Those populations and their respective economies could potentially be quite negatively influenced if sea level rises. And then thermal expansion also contributes to this because as the Earth's oceans warm up, water starts to expand. And water doesn't expand a ton when it warms up, but it can expand a little bit. As those water molecules start to heat up and approach the vapor phase, they're starting to sort of take up a little bit more space. And so this is what's happening to the Earth's oceans as they are warming up. So we can actually look at some data illustrating how this is happening going back about over 100 years. And what we can see is that there has been a pretty significant cumulative sea level change since the late 19th century, and an average increase of about 0.15 inches per year in global sea level increase. Now, that might not seem like a lot, but if you start to add up 0.15 inches per year times a whole bunch of years, we can see that if we continue projecting this into the future, that the Earth's sea level is certainly probably going to rise quite a bit if the temperature of the oceans starts to increase significantly. And this is, of course, directly related to greenhouse gas emissions because as greenhouse gas emissions increase, that causes the Earth's atmosphere to have higher concentrations of those greenhouse gases, which causes global warming, causes the greenhouse effect to make the Earth's atmosphere warmer, and that can directly cause the Earth's oceans to get warmer. And so what we can see are various projections in how sea level rise is expected to happen in some different greenhouse gas emission scenarios, kind of like we saw before. We could have low emission scenarios, intermediate scenarios, or really high emission scenarios. And of course, with increasingly higher emission scenarios, we predict that the Earth's ocean, that sea level rather, is going to increase quite significantly. And this is what the data looks like up until about the present moment. Sea level hasn't risen a ton, but it certainly has. As we already know, it's been rising since the late 19th century. And what we can see is that if we don't do anything about decreasing greenhouse gas emissions, that sea level is projected to rise quite a bit in, say, the next 80 years or so. And in fact, the rate of sea level rise could increase as much over the next 30 years as it has over the last 100 years. That's a pretty rapid increase in sea level happening as a direct artifact of our burning of fossil fuels that cause large concentrations of greenhouse gases to be released into the atmosphere. So sea level rise is yet another artifact of climate change that often gets discussed by climate scientists. And of course, climate scientists, when they think about impacts of climate change on the Earth's oceans, are very concerned with ocean acidification. And ocean acidification is something that basically happens when carbon dioxide becomes dissolved in water. And this might sound strange, but when carbon dioxide is dissolved in water, it makes water more acidic. And it does this by increasing the concentration of hydrogen ions in water, thereby lowering the pH of water. If you don't know this, pH is a measure of hydrogen ion concentration. And really low concentrations of hydrogen ions lead to really acidic conditions, and really high concentration of hydrogen ions lead to really basic conditions or high pH. And so how does this work? Well, carbon dioxide can react with water and carbonate ions. And if that reaction proceeds, then this acid, this weak acid bicarbonate will form. And as it turns out, carbonate ions also are important for forming another compound known as calcium carbonate. And calcium carbonate is what shelled organisms use to form their shells. But carbonate ions have a little bit of a higher affinity for forming carbonate than they do for forming calcium carbonate, or forming bicarbonate than they do for forming calcium carbonate. So carbonate will react more readily with carbon dioxide and water than it will with calcium. What does this mean for calcareous or shelled organisms? It means as the concentrations of carbon dioxide in aquatic ecosystems goes up, there is less carbonate available for them to basically build their shells because that carbonate is getting sucked into a chemical reaction that forms bicarbonate. And this is happening because of the process of ocean acidification. And so this can cause, for example, a loss of fitness in shelled organisms that happen to occur in increasingly acidic conditions. We can kind of see examples of that here, where there is decreased calcification with increasing acidity. And so this can have a pretty negative impact on ecosystems where calcareous organisms are a major component, such as in coral reefs, where these corals need uh, carbonate ions in order to create calcium carbonate in their bodies. And when there are not very many, when there are not as many carbonate ions available, it can contribute to the process of coral bleaching. And this is also exacerbated by rising sea temperatures because rising sea temperatures tend to make habitat less suitable for the algal symbionts of corals. And so sort of the combination of ocean acidification and increasing ocean temperatures kind of leads to decreases in the uh, success of these different kinds of organisms. Healthy coral ecosystems start to decline and ultimately die. And we're seeing this happen in a lot of coral reefs throughout the Earth's oceans. And this is directly related to human-induced climate change patterns, particularly related to increasing concentrations of carbon dioxide in the atmosphere and increasing global temperatures caused by global warming. And ocean acidification is kind of only really projected to get worse with climate change. So again, if we think about these various climate change scenarios, we can look at what the present condition of ocean acidification is. The situation isn't horrifyingly bad yet. And if we start reducing carbon emissions by the end of this century, the situation might not be super terrible. But if we just continue burning fossil fuels at our present rate and don't reduce carbon emissions in the atmosphere, we can see that the ocean is projected to become very, very acidic, as shown by the color on the scale bar here, going from very acidic to relatively more neutral pH to relatively more basic. I shouldn't say neutral pH, but more acidic to more basic. We can see that with no decreases in carbon emissions, the Earth's oceans will become very, very acidic. And the effects of ocean acidification could turn out to have bottom-up effects in marine food webs. So as calcareous organisms are having decreasing access to carbonate ions because those carbonate ions are getting sucked into different chemical reactions that form bicarbonate, those organisms will probably have decreasing success. And then other organisms that depend upon calcareous life forms for food will find themselves struggling for food. And so we can see that things like shellfish or pteropods or zooplankton that form the basis of some important marine ecosystems could ultimately decline, leading to declines in the kinds of animals that depend upon those things for food. So there are a lot of negative impacts that are likely to happen in the Earth's oceans as a result of climate change, and that is mostly related again to ocean acidification caused by increases in carbon dioxide concentrations in the ocean. What can we do about this problem? Well, reducing carbon emissions is certainly a first step forward in the right direction. And there's also this effort to try to capture carbon and sequester it. And this has been proposed as a very real climate change solution. And so, for example, folks might take certain carbon emissions and instead try to trap them below ground as opposed to allowing them to enter the Earth's atmosphere, effectively capturing them within the Earth's surface, within the interior of the Earth. Likewise, planting trees, planting photosynthetic life forms on the surface of the Earth is an effective way at capturing carbon because carbon dioxide gets taken up by plants. They need it for photosynthesis, and photosynthetic biomass can hold on to a lot of carbon and prevent it from entering the atmosphere. And even dead and decomposed plant matter can still hang on to a lot of carbon dioxide. And so efforts to try to increase the amounts of green space, particularly in urban environments where there are a lot of carbon emissions, can help decrease those carbon emissions. And then in aquatic ecosystems, promoting the growth of things like kelp forests can be really effective at capturing carbon. So in marine ecosystems, when carbon dioxide is dissolving into the water, photosynthetic life forms in these marine ecosystems can take up that carbon dioxide and prevent ocean acidification. So there are efforts that can be taken to try to reduce carbon emissions. Unfortunately, the average person probably isn't thinking about this a whole lot. The average person is probably trying to get by in their day-to-day life and may or may not even have a choice about depending upon fossil fuels as an energy source. But by and large, our dependence upon fossil fuels as an energy source is directly related to exacerbating the effects of climate change. And we, again, already know that we're in a warming period naturally. It just turns out that we're making the warming worse by relying so heavily on carbon-based fuels for energy. And so the situation, again, is very daunting and very real, and it's something that folks should be focused on, and we should be trying to coordinate our efforts somehow or another, not just as members of one society, but really as members of an entire planet, as members of a single species. We should all be thinking, what can we do to prevent these kinds of projected scenarios from really going completely out of control? How can we keep our Earth's carbon dioxide concentrations from reaching these ridiculous levels like 1,200 parts per million, for example? How can we prevent the Earth's oceans from becoming so increasingly acidic that marine ecosystems can no longer flourish? How can we prevent the Earth's sea level from significantly rising so much? So these are all questions that folks in the 21st century have are presented with. And it's easy to ignore them, but that doesn't mean that the problems aren't there. They certainly are, and there is overwhelming scientific evidence to show that the problem is there, and there is quite a bit of scientific evidence to show how bad the problem could become if we don't do anything about it. So this is something very serious to think about in the context of not only the survival of our own species, but the survival of many different life forms on our entire planet as we know it. So that is a sort of brief look into the world of climate change, how it happens both naturally and how human influence can make this problem even worse. And I invite you to try to think about these things because they are very serious realities that are likely to be quite impactful here in the 21st century. So that's it for this video. I'll see you next time.